So when I design local exhaust ventilation system in that particular room, I'm indirectly designing general ventilation also. Because you see, the general ventilation is like an energy balance of a particular space, right? I have energy going out, exhaust ventilation, then I have to bring in the energy to come in. All right. So now I'm going to start off by tackling all these emission at the contaminant emission or the heat sources at the emission point. So I work on the local exhaust ventilation system. Now I have, assuming that I have about 2000 or 3000 or 4000 CFM of exhaust going out. Then that's done. Step 2. I'm going to ask all these questions to myself. Okay, wait, what is the pressurization I'm going to maintain in the room? Okay, this room is dealing with products, food products, or it's dealing with wet products, whereby suspension of air from outside, it's going to have an issue. It's going to have an impact. Suspension of air from outside is going to bring in particulate aerosol, particulate dust, particulate aerosol, which is going to suspend in the product. So I decide I'm going to run this room on a positive pressure. Oh, I need a much higher stringent quality of air. Okay, I'm going to convert this into a clean air, clean room, right? And what's not. So it all subjective. So you, depending on what exactly is your requirement of going back to the basics of what's being emitted and what exactly products you're going to work on and what's not. You see, so I decide on the pressurization. Pressurization should be maintained within 10 to 15%. 10 to 15%. You see, because why the 10 to 15% is very important. When you have a local exhaust ventilation system design for the 3000, 2000 CFM, when you do not have adequate amount of air coming in, you can maintain 10 to 15% vacuum. But if you maintain 100% vacuum by not installing any makeup air at all, that fan is not going to function. It's not going to pull that 3000 CFM which you have designed for. There's no air to pull. So this is another basic, this is another cardinal, a very big error a lot of system providers make when they install a local exhaust ventilation system. They decide not to add a makeup air, not to add a supply air system. So what happens is the room becomes under extreme vacuum and infiltration. You see, just because you decide not to add makeup air or supply air, that doesn't mean the nature is not going to pull the air to come in, because you are running the room under extreme vacuum, 100% exhaust based on 100% exhaust ventilation. So air is going to come through the air passage from the gaps under the door, from the window seals, and what's not. So that is why it's important to maintain. And fan curve probably has been designed to operate based on the static pressure and the flow rate or what's not. But the fan is going to struggle because there's no air. So imagine this is what's going to happen to the fan which runs under 100% vacuum or without makeup air. Yeah? The fan is designed to run at 5 kilowatt to generate to 5000 CFM of air under 3000 Pascal or 300 or 400, 500 Pascals of static pressure resistance. Now, you do not have makeup air. You do not have, the moment you start the fan pulls all the air out from the room, then after that it doesn't have an air. You see, the air which comes through the window seals and the gap from the door takes a very long time. See, so what happens? But the motor has been given a mandate. You got to pull that air, you got to pull that 5000 CFM so that you and overcome the resistance of that 500 Pascal. It is being mandated in that manner. You know what it does? It's very disciplined. It's going to keep pushing. Hey, you know what? Okay, there's no air. Let's keep pushing it. So it's going to start incurring more current. So the motor is going to run at a higher load compared to how it was designed. So the wear and tear is going to increase. The motor basically is not going to last longer. You see? And what's not. This is exactly what happens when a motor runs through a friction problem, rotating issue, when the bearing is not well taken care of or not well maintained, or the bearing basically is failing. The motor will keep thinking that my work is to rotate at 1000 RPM. So it will going to keep rotating. So when the bearing fails and it's still pushing to fail, so it's going to pull more energy from more current to push. That's how it gets overloaded and gets tripped. The current gets overloaded and tripped. Now coming back to to the local exhaust ventilation system again. So we know very, very well that when you have exhaust, you must have makeup. So going back to the fundamentals of ventilation design again. All right, so this is how it works. So you create the local exhaust ventilation. But now, assuming that you are not going to use local exhaust ventilation system because the process is basically very scattered in all around the room, then opt for a general ventilation. See, opt for a general ventilation. But when you opt for a general ventilation, you see, or even with using the LEV and GV, the movement of air, if your fume hood is going to be on the other end of the hall, ensure that your supply comes from the left side. Air movement happens from the left to the right. If your contaminant has higher density, or very much depending on the specific gravity, it's a type of contaminant where even though it evaporates, it's going to basically suspend at the lower towards the floor, then your exhaust is going to be down, your supply is going to be top. Or it's a type where highly volatile and there's a lot of people working by basically at the direct vertical trajectory of the movement of air. You see, local exhaust ventilation function is to remove the contaminant away from the breathing zone, right? So do you want to introduce GV system which moves the air to the top if the contaminant is directly below the nose of the particular person? So you got to look into that element, that factor when you're designing too. You see, so you got a movement of air, you got LEV, you got pressurization. Now, once all this has been decided, then only we move towards cooling load. So there's another service, provision of service which confuses this entire ventilation. Air conditioning. Say in Malaysia we don't heat air, we usually cool the air. Air conditioning. Air conditioning comes at the last stage, the cooling load introduction. You see, I need to refrigerate. I need to use refrigeration process to cool the air. That comes at the end. You need to determine all these factors in the very first beginning. You see, because now when it comes to cooling, now first of all I need to calculate. I need to see what is my concern in the room: heat, chemical suspension. Then right after that I'm going to use LEV or GV. Then pressurization in the room, and then movement of air from left to right. Where am I going to put the exhaust grills? Where am I going to put the diffusers? Where am I going to put the LED? All this comes into action. So once I've done all this, then finally I'm going to look at what sort of temperature I'm going to maintain in the room, what sort of relative humidity I need to maintain. Again, process conditions and what's not. What sort of, am I going to use an AHU? Am I going to use a ducted ventilation system, or am I going to use a split unit aircon, or am I going to use the kind of a fan coil unit or whatever? So this comes towards the end. But even then, all these are interrelated, because now let's look at cooling load. What is cooling load? Cooling load is the exercise, is the mechanism or the parameter we use to calculate how much heat is being generated in the room, so that we can supply the adequate amount of coldness or adequate amount of energy to convert that heat into, or to mitigate, or basically to create air change. So basically what we are doing here is to cool the air, right? We put it in layman terms, to cool the air. So cooling load calculation takes place in a similar process. Once you have calculated GV, LEV and what's not, now number one, you calculate what's your internal load. Is there a heat product? How many people are there? What sort of heat they are generating? What's your light watts are? Okay, calculate your kilowatt per hour per day. You calculate your kilowatt per hour per day, or you can use your BTU per day, but depending on what English unit, metric units you're going to use in your design. Then you move on from there. You look at transmission of air, hot air coming inside, your type of wall you're using. You see the type of insulation you're using. You have to calculate the transmission load. Your solar energy coming in, the type of window you're using. There's a U value. U value is basically dictates the movement of heat from one space to another space with the wall in between. You see, so there are U values being given by the manufacturers. There are U values recommended by guidelines like UBPL and what's not. So you have to calculate the transmission. So you got the transmission load, you got the internal load which comes from the people, from the light, from the products. Then you have the air infiltration load. You see, you have calculated your GV and LEV earlier, right? You have calculated your air changes, your internal velocity and what's not. So you have to plug in those numbers, air infiltration, into the cooling load. You see, so you have these three elements, all right? Then you calculate your total cooling load, then you size up your air conditioning system. So that's how you complete the entire ventilation system. All right. So again, to summarize, ventilation system is the matter of how we use this air movement and reach the objective. But your objective has to be very, very precise. Clarity of your objectives is important. Your design approach will move on based on the clarity of your design, of your objective. You see, so do not get too confused or create limitation based on this AHU, GV, LEV terminologies and what's not. The functionality is very much depending on your objective. Use these terminologies to be a upper hand or to be supporting you so that you can apply the mechanics in a much effective manner. Let's work towards a good ventilation system. Good day. Bye-bye.